So far, we've only discussed how descriptor models can be used to understand activity for a single reaction. But as we've seen previously in the course, real systems almost always include multiple reactions. When multiple reactions are present, maximizing selectivity to desired products becomes important. So let's see how descriptor models can be used to understand and predict selectivity. In the last video, we looked at an activity map for CO hydrogenation to methane. Here, the rate was a function of two descriptors, the binding energies of carbon and oxygen. The reaction of CO and hydrogen over metal surfaces, however, can produce many different products. This is where this combination of CO and hydrogen gets its name, syngas or synthesis gas, because so many different molecules can be made from it. So here let's just consider two others, methanol and ethanol. Just as we did for methane, activity maps for methanol synthesis and ethanol synthesis can be generated. So in the first three panels here, we have activity maps for methane, methanol, and ethanol production as a function of those same two descriptors, the oxygen binding energy and the carbon binding energy. The methane activity map looks slightly different than it did in the last case because inclusion of these different reaction pathways gives us different routes to getting to methane. So here, if we want to construct a selectivity map to understand selectivity to these different products over metal catalysts, we can write the selectivity to any one product, we'll say J, as the rate of formation of that product over the total rate of reaction, so the rate of formation of all products. So essentially what we're doing is dividing the activity map for producing one product over the sum of all the activity maps. So if we do that, we get a plot that looks like D here in the bottom right corner. So this map provides insights into what catalysts are selective for a given product. So we can see on the right here, this green region, a group of catalysts that are selective for methanol production, which bind carbon very weakly. So this includes copper, silver, and gold. We also have a region of catalysts which are more strongly binding to carbon, which are selective for methane production. And finally, we can see that the region where selectivity to ethanol would be predicted is very small, and it also occurs in a region where no monometallic catalysts lie. So this explains the observation that no catalysts have been found which are highly selective to higher alcohol synthesis. So now we've seen how descriptor models can help us not only understand activity for a single reaction, but also selectivity when multiple reactions are present.